to forget that again. I mean, I might, but. Okay, so one thing that I want to point out is that there will be a second midterm next Friday, which is going to be October 9th. So not the 2nd, not this Friday, but the next Friday, there will be your next midterm. And the structure of the midterm will be pretty much exactly the same as the first midterm. Pretty much no difference in structure, just difference of material. I'll send out an email probably on Monday about that stuff. Any questions on that? Okay, well, it's not cumulative. So it won't be cumulative in the sense that I won't directly ask you to use or to prove things about logic and things like that, and there won't be truth tables. But of course, the logic kind of underpins all of our proof strategies. So it's not, you know, cumulative in the sense that you should go back and look at problems from chapter 1, but this class does build quite a bit on the material in chapter 1 and chapter 2. Does that help? Yeah, sure.
I have a quick question about studying for the exam.
Mm-hmm.
So obviously you can't give us all the problems in the textbook for homework. And I was
Right.
wondering if there are any particular reason you assign specific problems and how going from there so we can study a little bit better from the textbook.
Yeah, I tend to assign the problems that I find less boring. There are a lot of problems that feel like busy work, which are good to do, and I assign some of those. But in general, I tend to assign problems that maybe showcase something slightly different about some topic, or kind of force you to expand the way that you think about a given topic. So honestly, I'm kind of motivated by interest, like how interesting a given problem is, and I try to assign more interesting problems. I don't know if that's a very helpful thing to do. One thing to remember in studying for this material is to remember the special cases, so to speak. So for instance, when you're thinking about sets, there are these kind of special cases that you always have to keep in mind, like the empty set is always a subset of any set, or the entire set is always a subset of any set. One thing that was very important to remember on the first exam was to remember about 0 being inside the real numbers or the integers, because that would kind of change the way that you thought about some of those true or false problems. So I guess those are some things to keep in mind, kind of these special cases that always come up, but maybe you don't spend a lot of time thinking about.
Okay, thank you.
Yeah, it's kind of long-winded. I don't know if that was helpful at all. Any further questions? Okay, great. Let's begin. So last time, and now I'm kind of unsure about last time because I didn't lecture last time, but I believe Sarah discussed relations. Can someone tell me what a relation is?
A subset of the power set of a set?
Close. It is a subset of the Cartesian product of two sets. A cross B. So a relation from A to B is some subset of this set that you have here, right? And we're going to see a lot more about relations going forward. Actually, maybe we'll get to an application of relations today. This okay? Yes, thank you, Morgan. I wasn't reading the comments. Okay, so we discussed relations. We also discussed unions. And I think Sarah gave you some pretty general unions. We'll go over those again, and intersections. And once again, from what I remember, she gave you some kind of challenging intersections. We'll go over some of those a little bit again today. Any other particular things that were discussed last time on Monday?
Disjoint relations?
You mean when sets are disjoint?
Yes. But
Yeah,
we pretty much only got a definition, and that was the last thing we did.
great. Disjointness for sets. And what is the definition of disjoint? So A and B are disjoint if, what's the definition again?
If the only thing they have in common is the empty set.
Right, if A intersect B is equal to the empty set. Or in other words, there's no element that they have in common. Excellent, great. Okay, so what we're going to do today is we're going to kind of continue on with a bunch of definitions of things that you can do to sets, and do with sets. Okay, so starting off, let's give another definition. So the difference, the set difference of two sets of A and B, which is written A with this slash B. Sometimes it's written A minus B, but I dislike this notation, so I will almost always, and I hope the answer is always, write it in this way. I dislike this. Okay, so A set minus B is going to be the set of all elements of A not in B. So for instance, if I set my set A to be equal to 1, 2, all the way up to 10, and I set B to be equal to 5, 6, 7, all the way up to 15, what is A set minus B? So this is a 5 and so 5 and 6 do appear inside B, so they'll be subtracted essentially. So yeah, I'll end up with 1, 2, 3, 4. Good. Yeah. And we can also go the other way. I can also ask what B set minus A is. Right? I can still ask what are the elements in B which are not elements of A, and what do we get? Maybe I should write more clearly. 7, 8, 9, 10, 11, 12, 13,
It'll be
14.
15.
Yeah, it'll be 11 to 15. Sorry, maybe this came from me writing out these things really poorly, but here it'll be 11, 12, 13, 14, and 15. I take precisely the elements of B, which do not appear in A. So 5, 6, 7, 8, 9, 10 all appear in A, so those get tossed out, and then this is what's left over. So one important thing to note is that set difference is not, this is not a symmetric operation. So in general, I would expect to get very different things by examining A set minus B versus B set minus A. So in these finite examples, is this kind of clear or reasonable? Any questions? Of course, we can do more interesting things. And by interesting here, I mean usually infinite. So for instance, I can also take R set minus Q. What is this going to be? Yeah, exactly. This is precisely the irrational numbers. I don't have a symbol for them, that's fine, but it's still a well-defined set. And it's defined in exactly this way, right? And this notation is precisely how we defined the irrational numbers. They are the irrational numbers, or they are the real numbers which are not rational. Okay, so these are the irrationals. How about Q set minus R? If I look in the other direction. Oh, that was these are some excellent R's and some reasonably good Q's. What's this? Yeah, here we get the empty set. I will write it in this way, but the empty brackets is also a reasonable way to write it. This is the empty set. Any questions on this? I think this is reasonable. Okay, we're just gonna continue smashing through definitions. So one thing that we often do, so often, we specify some sort of universal domain. U. And so one nice example of this is that when you're working with the real numbers, for instance, like we have all of these questions that are like, what are the intersections of all these intervals, or what are the unions of all these intervals, or what are the unions of all these sets where the sets are subsets of integers? And the point is that all of those can be seen as subsets of the entire real line. And so it's a reasonable thing to take the entire real line as this kind of universal domain for a certain collection of questions. So essentially, when you have a question about a bunch of sets, and all of the sets are contained inside some natural universal set, it's reasonable to take that as a universal domain. That was kind of a hand-wavy discussion of universal domains, but we'll see how they're used. When we have a universal domain, we can define complements of sets. And the definition is just using one that we already have seen. The complement, so given a set A and universal domain U, and so necessarily A is a subset of U, otherwise U cannot be used as a universal domain. It doesn't need to be numbers, right? Our sets can be more general than numbers, but it's correct that it's a domain such that all of the sets that you're considering are subsets of that universal set. Yeah. So given a set A and a universal domain U, we define the complement of A. Which is written A bar. There are some other notations, but probably we'll use A bar. And it's exactly that, yes, perfect. Which is defined to be U set minus A. Great. So this is the sort of thing where what's an example of using complements? Here's an example of using complements. So let's let U denote the set of all things. And then what I can say somehow is that everything is either a banana or not a banana. And essentially what I'm saying here is that there's some set B, which is the set of all bananas. And then, of course, what I'm just saying here is that if I take the set of all bananas and I union that with the set of the complement of bananas, this is the same thing as bananas union U minus bananas, this is equal to U. So everything is either a banana or it's not a banana. So you just take your whole universe or your universal set U and you break it up into one set and its complement. This is an example of complements. All of you are complements of bananas. Congratulations. Or in the complement of the set of bananas, I shall say. This is kind of a not rigorous example, but it's still a good one. There are more interesting ones when we start thinking about examples that we've already seen, right? So what's the complement? So if we set R to be our universal domain, then what is Q bar? Yeah, it's the rationals again. Similarly, what is Z bar? There's not really a nice name for this, but can someone kind of describe what Z bar is? Fractionals is an interesting way to describe that. It's not objectively incorrect, but you have to remember that you're going to be taking fractions where some of the fractions are irrational numbers. And then you also have to exclude all of the cases where they end up actually being Z. So maybe a different way of writing. I mean, there's no like name for this set, but what this is going to be the irrationals union with the rationals such that in lowest terms, the denominator is not equal to 1 or negative 1. I think this should be a way of capturing the fact that I'm dealing with rational numbers which are not integers. Right, exactly. The it's true that the best way to describe this set is just the non-integers of the reals. Like that's somehow the best thing to say. But if one wants to discuss kind of atomically what is inside this set, the complement of Z, then one should mention these things. But you're right. The best name for this set is the non-integers in the reals. Any other questions? Great. Now there's T all over my paper. Okay. Okay, so that's complements once we have specified a universal set. I'll repeat one more time. This is a place for me to stop and see if there are any questions about these definitions that we've put together. Oh, one last thing to notice is that obviously these things depend heavily on what the universal domain is, because if my universal domain was Q, then Z bar inside Q is a very different thing from Z bar inside the reals, right? Okay, so this notation depends heavily on the universal domain. Okay, so now, in a very similar way as we did with logic, there are just a huge number of set identities that we can play with now that we have these definitions of unions, intersections, complements, etc. And the way that these are all proven comes directly from logic. So all of them have the same names as a technique in chapter 1. And actually, there's a dictionary where you can go back and forth between sort of set language and logic language, which I'll discuss in a little bit after I go through some of these set identities. So assume U is a universal set, and then A, B, and C are subsets. Then we have this long list. A intersect the universal set is equal to A. A union the empty set is equal to A. And these are going to be called the identity laws. Or identity relations, maybe. I don't know. I'll just write identity. Similarly, we have A union the universal set is what? Actually, I'm going to have all of y'all answer all these questions because that's a reasonable thing to do. Yeah, A is a subset of U, so the union of A and U has to be U. And how about A intersect the empty set? What are the common elements of A in the empty set? Yeah, there's nothing in there. So these are called the domination laws, or identities, or rules. I don't know, whatever you prefer. Excellent answers, everyone. We have idempotent rules or laws, or identities. Obviously, I have no idea what to call these things. Okay. What is A union A? Yeah, this has to be A. If any of you are cheating and looking in the book, you got to stop right away. What is A intersect A? You have to think about all of these. I can't tell if anyone's writing anything different, but the answer is always also A. The common elements of A and itself are itself. Really motivating stuff here. We have the complement rule or law, which says, okay, I'm going to take the complement of a set, and then I'm going to take the complement of that thing. What should I get if I take the complement and then I take a complement again? Yeah, I should get back A. I can view this, it's a complement. I can view this as the following kind of sort of Venn diagram. If this is U and A is some subset here, then this is A complement. I just take everything in U that's not in A. But then if I take the complement of A, or of A bar, then I take everything in U that's not in A bar. So this is also A bar bar, right? Does that kind of make sense? I wish y'all had those like clickers, and so I could make y'all vote on something, and then the answers would be like A and A bar and B and C. And then I'd check who's sleeping. No, I wouldn't do that. It's fine if you're sleeping. Okay, let's do some of these ones. A union B is equal to B union A, because the way that we define this didn't have order mentioned at all. A intersect B is equal to B intersect A. These are some commutative laws. Before I go any further, I'm kind of halfway through this long list, and they all look kind of very similar to the things that we found in in logic. So can someone guess at a dictionary or a way of passing from these statements to statements in logic? What does the last identity say? This says A intersect B is equal to B intersect A. So order doesn't matter when you're taking unions or intersections.
I was referring to what it was called. Sorry.
Oh, commutative. Clearly I failed second grade and never learned how to write. Now I'm a teacher.
Your question was how to go from these identities to logic identities?
That's right. Yes, so union would be and intersect would be or. Very good. So union goes to and, wait, sorry. Union goes to and, intersection goes to or, and then A, the set A, goes to the property P, which is equal to X is an element of A, right? So then what, if this is the translation between a set and a proposition, then how do I get a tautology? No, this is incorrect. Union should be or and intersection should be and, right? Union is true if an element is in A or an element is in B, and intersection is, this is true when X is an element of set A and an element is a set in B. Yeah, probably y'all were yelling at me on chat to do this.
So
Okay.
your tautology would be set A union set A.
So I was thinking that the tautology would be X is inside the union, or sorry, inside the universal set. So U would go to the set, or would go to the proposition X is inside U, but everything is inside the universal set. So the union goes to true, and the empty set goes to false, because the statement X is inside the empty set is always false. Then A union A would go to something like P or P is equivalent to P, right? This statement would become P or P is equivalent to P, and P and P is equivalent to P.
I think I meant to say A union A bar.
Ah, right. A union A bar would be something like true or false is true, and that's correct. So yeah, you'd be right in making a tautology like that. That's correct. And that can be viewed as A union A bar is the universal set. Yeah. So this translation is kind of cool. We won't really exploit it or use it very much, but I just want to really point out that all this machinery or all these things that we're doing for sets are really just thinly veiled translations of things that we know for logic. And with that enjoyable remark behind us, I'm just going to keep on writing this, massive list. Best kind of education. Okay, the next one should be the associative rules or the associative laws or propositions. So A union B union C, C is equal to A union B union C, and similarly A intersect B intersect C is equal to A intersect B intersect C. These are associativity laws. We have distributive laws, so A union B intersect C is equal to A union B intersect A union C. And similarly, A intersect B union C is equal to A intersect B union A intersect C. So these are distributive. We have De Morgan's. So remember, De Morgan's had to do with negation. And in this translation between logic and sets, negation is the same as taking the complement, right? So De Morgan's will give us A intersect B complement is equal to complement of A union complement of B. Once again, when you negate a compound proposition, you change the sign. That's exactly what's going on here. And similarly, A union B complement is equal to A complement intersect B complement. And we can prove one of these. I think we'll prove one of these, and then the book proves the other. De Morgan's. We have absorption. A union A intersect B is equal to A, and similarly, A intersect A union B is equal to A, absorption. And lastly, A union A bar is equal to the universal set, and A intersect A bar is equal to the empty set. So these are complement laws. And if you translate these back into the language of logic, then this is saying something like P or not P is true, and P and not P is false. Okay, that was a long list, and on one hand, I know that you all have fear in your hearts that you'll be forced to memorize this whole thing for the next exam. And I'm here to say, don't have such fear in your hearts. I will just make you practice it so much that it'll be memorized already. So there's no need to fear. Also, it's not so bad because all of these are essentially direct translations of the logic identities that you've already practiced. But nonetheless, we should prove a couple of these. Before I go on to prove anything, though, does anyone have any questions? How are you doing on time? 15 minutes. Okay, let's prove one of these. Let's prove that A union B complement is equal to A complement intersect B complement. Okay, first rule is, how do I prove an equality of sets? So here in the side, how do we prove equality of sets? What does it mean for two sets to be equal? That's true. Two sets are equal if and only if they have the same elements. And the way that we prove that is, and I'm going to make everyone repeat after me like 3 times. We use a double inclusion. I'm going to type this. To prove an equality of sets A and B, use double inclusion. That is, you prove A is a subset of B, and then you prove B subset A. I'm trying to, okay, now I'll do it on the page. Prove a double inclusion. A is a subset of B, and B is a subset of A. There are two things that you have to prove. Everyone repeat this to yourself like 3 times. To prove an equality of sets, you prove a double inclusion. A is a subset of B, and B is a subset of A. I'm being a demagogue here. This is one thing that you should remember. This is how we prove something as a subset. Right. How do you prove that something is a subset? If you want to prove that A is a subset of B, you must show that for every element of A, that is X in A implies X is in B. And I'll show you how it goes here. But at least this is, the idea is you start with an element in the subset and you show that it must be an element in the larger set. That's how you prove a subset. Okay, so there are 2 parts to this proof. The first thing that I want to show is that A union B complement is a subset of A bar complement or intersect B complement. Okay, this is part 1 of the proof. So if I'm trying to show something like this, I start off with let X be inside A union B complement. What does the definition mean if X is inside A union B complement?
Does that mean that X is inside A or B complement?
Well, just from the definition, what does it mean to be inside the complement of a set? Let's forget about the A union B and let's just remember A is inside the complement of something. So by definition, X is in U and X is not in A union B. Right? This is just the definition of a complement. It's in the universal set and it's not inside the set that's being complemented. So now we have to understand, how is it possible for X to not be inside the union of A union B? So Morgan, your statement is not quite correct. It's somewhat close to what we're going for, but X not being inside A union B, this is equivalent to X not being in A and X not being in B, right? Because if X is an element of either of these sets, then X will be an element of the union. So it's not the case that X is not in A intersect B. That's a weaker, like X being inside the intersection of A and B means that X is in both A and in B. But the thing that we want to negate, that is X is not inside A union B, is equivalent to, both of these. X is not in A and X is not in B, because if X is in either one of these, then it'll be inside the union. Is that okay? I mean, if you want to break it down even further, you can write down the definition of what it means for X to be inside A and B, right? This is the negate here. I'll do this in kind of a side note. X in A union B is equivalent to X in A or X in B. And then being not in means I want to negate this whole statement. So I'm negating X in A or X in B. And if I negate this, this is X is not in A and X is not in B. And that's what I have written here. Is this step clear? So now that I've separated out into two separate statements, what does it mean if X is not in A? Yep, if X is not in A, then it has to be in the complement. Since X is not in A, we have X is inside A complement. Similarly, X is not in B is equivalent to X is inside B complement. Since X is inside A complement and X is inside B complement, we conclude that X is inside A complement intersect B complement, because it's in both. So what I showed here is precisely this strategy. I need to show two inclusions. I started with one inclusion, and I started with an element inside the subset piece. I said X is in this thing. What does it mean for X to be inside the complement of A union B? Well, it means X is in U and it's not in A union B. This is equivalent to X is not in A and X is not in B. When I trace through all these collections of equivalent statements, I end up with X is in A bar intersect B bar, or A complement intersect B complement. So anytime that I have an X in here, X also appears in here. So I've proven this statement. Any questions here? Catherine, does this clarify a little bit about the strategy of showing that one set is a subset of another set? Great. You're welcome, Yo.
How is this proving that they're equal if we're only using X as one element?
So there are two things that I want to address. So first of all, this doesn't prove that the two sets are equal. This is only half of the story. So that's the first thing. And the second thing is that I'm not taking X to be just one element. I'm taking X to be an arbitrary element inside A union B, right? Like this argument that I use here holds for any possible X that's inside this set. So I'm not just doing this for one X, I'm doing it for an arbitrary X in this set, which in a certain sense, if you remember the universal instantiation and universal generalization laws, means that I'm doing it for all X's inside this set.
Okay, that makes sense.
Does that help a little bit?
Yes, thank you.
Great. So as I mentioned, this is half. What's the other half? Well, it's probably difficult to write in chat, so I'll just write it. This is the same thing as the complement of A intersect the complement of B. I need to show that this is a subset of A union B complement. Right? So let Y be an element of A complement intersect B complement. I start with an arbitrary element over here, and I show that any element over here must be over here as well. So I start with let Y be inside this set. Okay, what does it mean if Y is inside an intersection? By definition of intersection, yep, it's in both. So I get two statements out of this. I get Y is inside A bar and Y is inside B bar. And what does it mean for y to be inside A bar? That's right. Thus, y is not in A and y is not in B. Not in B. Okay, what should my next step be? That's right. This means that this implies that y is not inside A union B. Because it's not in this set and it's not in this set, so it's not in their union. And what does it mean if y is not inside a set?
It's in its complement.
Exactly. Thus, by definition of complement, y is inside A union B complement. In this case, it's a reverse of the first step because these are all sort of tautological, but in general, if you have some set equality, it might be the case that proving the two directions feels quite different. Here, they feel the same, but that's because of the kind of nature of the kind of things that we're proving. But yes, it's correct that this is essentially the reverse. So once again, the first thing that I did is I broke up a set equality into a pair of inclusions. I want to show this set is contained in this set, and then I show this set is contained in this set. This is how we show equality of sets, a double inclusion. Okay, that's step one to remember. And then step two is, how do we show that a set is a subset of another set? We pick an arbitrary element in here and show that it must be in here. And that's what I did here. And then I did the reverse process over here. I took an element in here and I showed that it must be in here. This concludes the proof.
Is there a particular reason why you decided to use two different variables?
For me, I use two different variables just to underline that you should not conflate this x with this y. But since these are technically two different parts of the proof, it's fine if you use x in both. You just have to remember that you're not talking about the same x objectively, right? Here, I have proven that x is in here implies x is in here for an arbitrary element over here. Here, I just need to say, pick an arbitrary element over here, show it's also in here.
Okay, thank you.
So right. I'm changing variables for maximum clarity and saying that here I'm dealing with elements that live in here first, and then I show they're in here. And here I start with elements that live in here first, and I show they live in here. And if I wanted to go all the way down to logic down here, essentially I could break it down into literally a De Morgan's, just like over here, right? This is this sort of thing like y or not y in A and not y in B, right? This is the statement. Thus, y is not in A and y is not in B. That's the same thing as the negation of the statement y is in A and the negation of the statement y is in B. And what is this equal to by De Morgan's? This is the same thing as the negation of y in A or y in B. And then I can translate this statement to a statement about the union. Thus, y is not in the union. So what I want to emphasize is that this rule for sets, which is called De Morgan's for sets, can literally be brought down directly using the definitions to the logical statement of De Morgan's. It matches precisely with the logical statement of De Morgan's.
We won't have to go into the logic like that for homework, will we?
On one hand, it's not a bad thing to practice. On the other hand, I would accept this as a correct proof. So the answer is this is sufficient for a proof, and you don't have to get down to the grainy, direct logic of it. But on the other hand, it's probably a good idea if you at least practice going from these statements to their definitions, right? What does it mean that X is not inside A union B? That's precisely equivalent to X is in A or X is in B, and I want to negate that whole thing. That's not a bad exercise to be comfortable doing. In fact, I kind of wish that I had done it all the way down to this, but this is still sufficient as a proof. Any further questions? It's 10:12. Y'all should head out and have a wonderful Wednesday. And I'm, of course, going to be here for a couple more minutes if anyone has questions.
Thank you.
Yeah, sure. Of course.
Thank you.
Happy to be chatting about math.
All right, I have a question. It's
Yep.
pretty simple. It's just I thought I'd catch on to it, but I didn't. So, what are like, just to repeat it, the symbols like Z, Q, and R? Like Z is like the counting numbers, basically, right?
Z is the integers. So
Including
this is
negatives?
negative, including the negatives. So -2, -1, 0, 1, etc.
And then that weird Q is just the irrationals.
Q is the rationals. The Q
Oh,
actually here is for quotient.
okay.
So these are all the things that can be written as quotients, P over Q, where P and Q are in Z and Q is not 0. In other words, it's a quotient of two integers.
Okay.
And then R is the reals.
So would the reals just include like irrationals too?
Yep, exactly. In fact, the irrationals are precisely the reals minus the rationals.
Okay.
This is the irrationals. The irrationals were defined in this way. They're precisely the real numbers which are not rational. And what's an irrational number that you know?
Pi.
Pi works, but what's